Okay, hello everybody, this is Dr. Hussein again in module number 3 for calculus and linear algebra. This module we will start discussing first order differential equation, and particularly in this week number 8, we are going to give a revision for the integration because we will use them in solving first order differential equation, and then we go through the terminology, principles, definitions for differential equation. And the first method to be discussed, the first two methods are the direct and the separable methods. This is related to course learning outcome, which is solve first and second order differential equations, which is the last one, the last course learning outcome. Now, you already study in level 1 semester 1 the mathematical foundation, the differential equations, and you started from the principles, from the limit, and then you went through the principal functions. As example, when it is ax to power n, this is the integration. It will be ax to power n plus 1 over the new power, okay, plus constant. We usually call it arbitrary constant, integration arbitrary constant. We learn how to integrate cosine, sine, secant, cosecant, and cosecant cot, secant tan, exponential, ln. All of this have 1 over n x to give ln. All of these have been discussed. Some here I try to pick some example just to refresh your memory. You can see here is the integration of constant. Directly it will be 8x plus the constant. Okay. Now, if I have many terms, as example 3x, 2x squared minus 5, then when I integrate, I will use the general form. It will be 3, you see here, 3x to power 2 over the new power. And I repeat the same thing, x to power 3 over 3 power, the new power. And this is constant, will be multiplied by x. But don't forget the arbitrary constant for the integration. Okay? If we have a fraction, we need to simplify. Okay, I mean separated, this is fraction and this is another fraction, and simplify, cancel, you are here, and then you can apply the formula to get the general solution. Don't forget, general solution contains c. We cannot find c unless you are given initial condition. If it is cosine, we know that integration of cosine is sine. If it is sine, integration of sine is cosine. If it is 1 over x, as example here 3 over 5, keep it outside, so we have integration of 1 over x, which give me ln, as you can see here. Okay, and if it is exponential, as you can see, 5 to be outside, constant, but if it is exponential, 1 over the power exponential 3x, and don't forget the arbitrary constant. Now, what if the function is not a standard function similar to the previous table, which is given in the previous table? We have three techniques, main techniques to be used. Either we use algebraic substitution, or trigonometric substitution, or partial fraction, or integration by part. Now I will try to pick example for each one at least of them. If you look to here, okay, you can see there is power. We cannot solve it directly because this bracket is multiplied 7 times. If we open it, it will be time consumed. But there is a way. By assuming what is inside the bracket to be u, I'm finding du over dx, and then back to substitute to convert the integration from integration with respect to x into, you see here, into integration with respect to u. It will be very easy to integrate because here you see it's a standard conjugate, mean u to the power 7 plus 1 over 7 plus 1, it mean 8. And don't forget the constant, arbitrary constant. Now let back from u again to x, as you can see here, back from u to x. So we will substitute this u by 2 minus 5, as you can see here, to the power 8. It's very simple. Okay. The second method is by using integration by using trigonometrics, where we are given table with 12, as you can see here, 12 different function. As example, if the function came is cosine square x, okay, the formula to be used is this. And the method is this, and the formula of the output will be this one. Or let me say, as example, 1 over a squared plus x squared. The output will be this directly. So if a function is similar to one of these functions, you can pick your output directly. Example here, I know how to integrate sine, but sine squared is something else. I go to the table. The table converted into this form. Now I can integrate 1, which is give me x, and integrate cosine, which give me sine. As you can see, it's very easy. Now, method number 3 is integration by partial fraction. You remember partial fraction from foundation. Here you have a fraction which is complicated. Using partial fraction, you are going to convert into simple separate fractions as similar to this. Now you can integrate. If we integrate them, this one will give ln and this one will give ln, as you learn from the standard functions. The last method is the integration by parts. Integration by parts, when we have function from different nature, as example, as you can see here, it's x and here is cosine x, different nature. Here it is t, here it is exponential to t. This is exponential function, this is normal function. Then we will use integration by parts, which deal with these type of problems. As you can see here, the formula is simply written this way: integration u dv equal uv minus integration v du. So let's specify where is u, where is dv. As example, in this function, I will assume that u will be x and all this part will be dv, as you can see here, dv. Then since I have u, let's find du. Du over dx will give me 1, and since we have dv, let's integrate to find v. We integrated, it is sine. Now let's substitute. We have u, we have v, we have v, we have du. We substituted, we are here. And integrate. It will give you directly the solution. Okay. Now, after this revision for integration, let's come to differential equation. I will start with the definition and let me say the terminology. Differential equation is equation already got derivatives. It means, as example here, as you can see here, dy over dx except this part. So y has been derivative differentiated with respect to x. Okay, so differential equation, which is simply called dE, okay, is the equation which caused let me say independent variable and dependent variable. The dependent variable was differentiated with respect to the independent variable. Okay, now this could be contain different function. We are dealing with exponential, cosine, sine, normal function, and so on. So you can see here are these are functions where here the function is y differentiated with respect to x. Sometimes we find y and x in the equation. Now if the equation contains more than one variable, as example y, but with respect to x and z and t, then we can differentiate it partially. We call it partial fraction. It means differentiate with respect to specific independent variable. As example, u here is a function of x and t and y, okay, while x and y are a function of t. We can differentiate u. You can see here, we can differentiate u with respect to x. It means keeping y constant. And we can differentiate u with respect to y. It means keeping x constant. The same thing here. U has been differentiated with respect to x and this with respect to t. Okay. Now, what about notation? Notation used for differentiation, either we use what we call Leibniz notation, which is dy over dx, d square y over dx, and so on. We go up for orders. Or we use prime, y dash, y prime, y double prime, or y dash, y double dash, and so on. Or we use subscript notation. As example here, it means that the function u is differentiated with respect to x. While here, the function u is respect first with respect to x and then with respect to y. Now what about the order? Order is the highest order of the derivative. As example, here in this equation, we can see d square y and here dx directly. So it seems to be the order of this equation is second order. Why? Here is first. Don't look to this power. This is power for the whole derivative. But here 2, it means it is differentiated twice. Y has been differentiated twice with respect to x. So this is called second order. Now, general form of ordinary differential with the normal one is the independent variable, the dependent variable that y dash, y double dash, and into the end equals 0. This is how it looks like the equation. Or we can represent it by d to the power n y over dx, because it could be first order, second order, and so on. Now, also one other property I would like to define here is the linearity. Linearity, it means the ordinary differential equation do not contain, okay, any sort of nonlinearity, things like square to the power 3, and these are called nonlinearity. I will explain with examples. Okay. Now, if you look to this equation here, this equation is dy over dt plus y equals 0. This is first order because, as you can see here, it's 1 times derived. Okay, it's linear. Why it's linear? Because there is no non-linearity in the equation. But if we look to this one is dx over dt. The variable is x. Differentiate with respect to t. But here it seems to be x squared. Square is non-linear, so it's sort of non-linearity. Now this one is dy. Y is my variable. Differentiate with respect to t. T to the power 2. Here t is the independent variable. So if it's coming to power 2, this doesn't mean it's non-linear because only we focus on the dependent variable. So this is linear. Here is sort of non-linearity. Why? Because y is multiplied by its derivative. This is sort of non-linearity. Okay. Now we define these. These, let me say, methods of notation. Y prime, double dash, and we can see in the different textbooks different way to present this. Okay, and their coefficients could be defined to be for each item there is a coefficient a. We call them a0, 1, 2, and so on. Okay, now these are examples of non-linearity. As you can see here, y dash will be multiplied here and here. So when we multiply by y, it will give non-linearity. Y, the variable, is the let me say angle of the sine. Sine is sort of non-linearity. Square here is non-linear also. Now next I will go to the degree. Okay, degree simply the degree of a differential equation is defined to be power of the highest order derivative. As example, if you look to this equation, the highest order is 2 because it's second order, but here it rises to power 1, so the degree is 1. The highest order here, okay, the highest order is 3, so third order differential equation comparing with this, and the power here is 1, so still it's 1. Don't look to this power 4 because it's coming to the first order, not the third order. Okay, now if we come here, this is second order, this is first order, but the second order rises to power 3 and here rises to power 4, so I will say okay, the degree is 3 because I look to the highest order of the differentiation. Now how we solve it? Okay, I can read here for the definition: any function phi defined on an interval I possessing at least n derivative that are continuous on I when replaced into n, the ordered or reduce the equation into an identity is said to be a solution of the equation on I. And simply I can summarize this to say, okay, solving differential equation is finding